Hello everyone again and welcome to the DMSI YouTube channel, and in this particular video we're going to continue from where we stopped involving collision frequency and determining this particular question. On our previous video we looked at how to determine the collision frequency, which is represented as Z. We had to take into consideration the volume of this particular collision tube, and then we arrived at using our relative mean speed to determine various other variables that will be taken into consideration, like the gas constants, the temperature, the molecular weight of that particular molecule, and also we took into consideration the number of particles in a stationary region. That it means that the particles are stationary in that particular tube, and also being able to look at how that one particle moving at that particular speed will collide with other particles. Some will be a miss, some others will be a hit, and as a result of that, at a particular time we're able to get a specific expression to be in terms of the number density that would then be important when we apply that to our gas ideal constants, and also introducing our Boltzmann distribution, which is around here, in order for we to re-express our collision frequency in terms of not only the pressure but also the temperature and other interesting variables that we are going to do and apply in this particular question. So in this question here, we're given various conditions and various limitations as well, but there are restrictions that needs to be taken into account, and so we're going to write that down and also check using units to confirm that our variables that are given actually will line up to the agreements and the units in order for we to get to our proper answer. So in here first we have our solution to this particular problem, which involves the following. We need to state the givens, and to state the givens in this question we are given the cross-sectional area to be 0.43 nanometers squared, and the next one here is that we're given the pressure to be equal to 12.1 kilopascals, and next here is we're given the temperature, which is equal to 217 kelvins. So a couple of things here to keep in mind is as follows. First is that the requirement for this particular question, what is this question asking me to determine, is actually to find the specific collision frequency, which is represented as Z. And what do we know Z to be? The unit for Z here is actually measured in per second. So looking at this per second, how are we going to determine per second? Let's look at those specific units that will have to align with our expression for the analysis part, and then we're going to see how that actually works with this particular question. So based on our analysis, we actually notice that since we're determining our specific collision frequency, we know that our collision frequency is determined to be 1. We need to note that it is the square root of 2 multiplied by our specific cross-sectional area multiplied by, in this case we're going to be using our specific expression for the mean speed multiplied by P, and this is all divided by our Boltzmann constant multiplied by our temperature. So looking at this here, we're going to actually rearrange some things. We need to take some things into consideration, like for example our R we're going to introduce very soon is actually equal to 8.314. Take note that the unit in here is measured in joules per mole times kelvins, and the next one here is our Boltzmann's constant, which is represented as this particular K, and it's equal to 1.38 times 10 to the negative 23, and the unit here is measured in joules per Kelvin. So looking at this here, let's figure out how to reduce this equation, simplify it first, and then play around with the units to see what we have before we put in our numbers. So what we see here is that for collision frequency, we have that particular C, which is represented as the specific mean speed to be expressed as square root of our 8RT over pi m, which is the molecular weight of that gas. So therefore, putting this in this particular equation, we'll arrive at our expression that agrees with the following variables in the question, and we'll be able to determine fully what Z is. So therefore, in this part, we have our new expression, which is now square root of 16 multiplied by RT, or divided by pi m, and this is now all multiplied by our cross-sectional area multiplied by P, which is the pressure, or divided by our specific Boltzmann constant, or multiplied by T at the denominator. So once we have this, we're going to rearrange this in terms of now using exponents, and what we see is that on the outside here we actually have temperature inside the square root, and we have temperature as well in the bracket. So let's look for how to play around with the exponents. And playing around with the exponents, we see that at the top where the square root is, our temperature is half, and this is divided by our temperature, which is 1. Therefore, this here is equal to temperature negative power, to the power of -1 over 2, which is pretty much, which means that our temperature will now be in the square root, but it will be at the denominator, not at the numerator. So as a result of that, we are going to actually re-express this by eliminating our temperature in the bracket, and therefore we're in the square root, we're going to have our temperature to now be in the denominator of our square root. So therefore this is going to be 16R, all divided by pi multiplied by our molecular weight, and take note that our temperature is actually inside, and this is all multiplied by the cross-sectional area multiplied by P over our Boltzmann constant. So let's look at now the units first. So for our units in the bracket, we're going to split this into 2 to actually figure out how to re-explain this. So in here we have our unit in our bracket, where our cross-sectional area, take note here, is represented as m squared, and in this case here we have to change now our units from nanometer to meters. So take note that the nanometer is in squared and our meter is also in squared. And the next one here is that our pressure, which is measured in kilopascal, we're going to play with pascals, which in this case we know that pascal is the same thing as Newton, all divided by our meter squared. And we know that our Newton is also expressed as the grams multiplied by our meter, all squared, by per second squared. So therefore in here we notice that in this particular part, where for our numerator we have our alignment taken care of, we are going to then combine this and this together to determine what the numerator is, and in this case here, by re-explaining this and introducing our kelvins in there, we are going to notice that, take note in here, that our specific expression is now shown to be called or expressed as kilograms meters squared, actually cubed, over meters squared multiplied by our seconds squared. So meters, we're left with 1, and all this is taken out, and what we have here, take note that we have our kelvins, which is our K, which is represented as the Boltzmann constant, is measured in joules, and we're going to introduce that on our next expression. So in here we have our numerator to be in kilograms multiplied by meter or second squared. And so introducing now our K, where our K, which is the Boltzmann constant, is actually represented as, in this case, joules per, in this case we know that it is measured in joules per Kelvin, we know that joules is actually measured in terms of Newton multiplied by the distance, and as a result of that, which is in meters, we know that Newton is represented as kilograms meter or second per second squared. So therefore this is going to multiply by m, and so we have in this case here to be in kilograms meter squared per second squared. Take note that we need to now combine these two together, because in here this is going to be the numerator and this here will be our denominator. So therefore, as a result, we have our numerator to be kilograms meter per second squared, and the denominator now is going to be kilograms at the bottom with meter squared, or divided by seconds squared. So once we have this taken care of, we are going to cancel as our seconds, and we're going to cancel our kilograms, and what we're left with is, in this case, 1m at the denominator. Therefore this bracket here actually has a unit that is in meter -1 to the power of -1. So once you have this noticed, our next one is how we're going to deal with the ones in the square root. Take note here that the one in the square root has the units to be expressed as, in this case, our r is measured in this particular joules per mole per kilogram. Therefore in this part here we per Kelvin, sorry. So therefore in this part we have our meters to be too long. So take note here that for our givens, we have our specific units for the cross-section area to be in nanometers squared. So therefore, to convert from nanometers squared to, in this case, meter squared, because we need to abide by the SI units, in this particular part, we are going to convert it to meter squared. So therefore, convert it to meter squared means that we know that 1,000, so we know that 10 to the power of 9 meters is equal to 1 nanometer. Therefore, for 1 nanometer squared, we'll have to square this, which means that we're going to have 10 to the power of -18 meter squared. And therefore, once we have this, we are now going to determine what the unit for our cross-sectional area will be now in terms of nanometer, from nanometer squared to meter squared. Therefore, we are going to multiply this number 0.29 by 10 to the power of -18, and we're going to have our new expression for our cross-sectional area to be 4.90 times 10 to the negative, in this case we're going to go one step back, which means 19 meter squared. So or you can actually express this as 0.49 times 10 to the negative 18 meter squared. So this is one number that we're going to use in this case in terms of the cross-sectional area. And then our next one we're going to deal with is how are we going to apply this particular givens in this particular question right here. So therefore, in this particular case, to solve, we're going to substitute our givens into our equation. Therefore, our z here is now equal to all square root of 16, and this is going to be multiplied by 8.314. Well, we're going to put the units down. So this will be measured in joules. We know that joules is a measure of the Newton multiplied by the distance, which is measured in meters. Therefore, we know that it is Newton is measured in kilograms per meter squared. Therefore, per kilograms meter per second squared. Therefore, this will be in kilograms meter squared divided by seconds squared. And this here is going to be divided by, in this case, we know that we have our pi, and we know that m, take note, is the molecular weight of nitrogen gas. Therefore, since we know that for one nitrogen atom, the weight of that, or atomic weight, is 14.01. Since we have 2, we multiply by 2, and that gives us 28.02. Take note, it's in grams per mole. Therefore, since it's in grams per mole, we are going to now re-express this in terms of kilograms per mole, which is going to be equal to 28.02 times 10 to the negative 3 for the unit in kilograms per mole. Therefore, this is going to be multiplied by, in this case, 28.02 times 10 to the negative 3. And take note that this is measured in kilograms per mole. And take note that we're still left out with, we're leaving out some other units for our gas constant. This is multiplied in this case by, let's extend this to reach out. This is now extend in terms of per mole and Kelvin. So since we have these units taken care of, we now have the other part here to actually take into consideration, which is the temperature. And we know that the temperature that is given is 270 kelvins. So therefore, we will be able to actually deal with this particular equation in a smooth manner. And on the other side here, we have our other expression, which is now in terms of our cross-sectional area. In this case, our cross-sectional area, take note, is actually expressed as, let's move this over to this side and let's drag this over here. So that will be helpful. So in this case here, our cross-sectional area, as we noted above, is shown to be 0.49 times 10 to the negative 18. So in here we have 0.49 times 10 to the negative 18 meters squared. Take note that this is going to be multiplied by our specific variable, which is called the pressure, and the pressure that is given is measured in kilopascals. So therefore, kilopascals means that you're multiplying by 10 to the 3. Therefore, our pressure, which is actually given as 12.1, is going to actually look like this: 12.1 times 10 to the 3 pascals. And we know that pascals is measured in Newton per meter squared. We know that the Newton is measured in kilograms per second squared multiplied by the meters. So therefore, we can now express our pascals in terms of kilograms, and we're going to see how this will help us to break this down into smaller units. So in here we know that this is going to be measured in kilograms. We have our meter, and this is seconds squared, that is for Newton, and we know that we're also going to multiply this by meters squared. So therefore meters cancels meter, we're left with 1 meter. And so once we have this taken care of, we have our other denominator, which is measured in this case K, and our K is the Boltzmann constant. The Boltzmann constant is represented as 1.38 times 10 to the negative 23. And take note here that the unit for this is actually looking up. It's measured in joules per kelvins. Therefore, joules is actually shown to be Newton, and we know that Newton is kilograms meter second squared. And since that is Newton, we're going to multiply that by meters, and this, take note here, is all divided by our kelvins, which is the temperature. So therefore, once we have this taken care of, we can now see some agreements that will be taken care of here. So our agreement in terms of units includes the following. We have our specific, let's move this here, we have our kilograms cancels kilograms, we have our specific mole cancelling out our mole, and what we have next is we have now expressing our square root region. We have our z to be equal to all square root of our numbers. When you put the numbers and you divide it on your calculator, you're going to get 6.96385. Take note here that we have our units to be in meters squared, and we have our other part at the denominator to be seconds squared, and finally we have our kelvins to be kelvins squared. And so on the other side here we have these numbers. Once you punch them into your calculator, you're going to have your constant, which is 3.77028. It's going to be too long, 99 times 10 to the 8. And take note here, our units here, once you align by cancelling out some variables, you have meter squared cancels out your meter squared, and next one here we have this meter cancelling this, and you're left with 1 meter. And then we have another seconds. Yes, we do have seconds cancelling out, and what we're left with is our variable now in kelvins. So this here shows that our kelvins will be way at the top, and it is at the numerator end. So therefore, take note here also that our kilograms cancels out our kilograms, and so what we're left with is this particular expression that actually shows us that, hey, there's still one more m, which is at the bottom right over there. So in this part, we're able to have our expressions, and by performing your square root for this particular segment, we have our z to be equal to 2.6389. Take note that the unit now is actually measured in meter per second kelvins, and this is multiplied by, in this case, 3.7702899 times 10 to the 8. Take note that this is actually measured in kelvins per meter. Therefore, we're going to cancel out various things, like for example our kelvins, sorry, let's change the color. Yes, our kelvins cancels and our meters cancels, and we're left with our units to be in seconds, -1, power of -1. So in this case here, our collision frequency, we're able to not only get our answer but also derive the unit, which shows that, hey, in this case our z, which is the collision frequency of nitrogen molecule at specific temperature, which is 217 kelvins, at our specific pressure to be around 12.1 kilopascal, which is the attitude conditions, which is in this case 15 kelvins. We know that this is actually, let's erase this to make it cleaner. Clean this up, and at 12.1 kilopascal, we'll actually have this number of particles colliding, or this particular molecule colliding with this many particles in that particular space, which is around 9.949 times 10 to the 8 in 1 second, which is massive. Imagine this, right? In 1 second, you're able to collide, or hit that many number of particles at that particular, in this case, collision tube. That is really impressive to see this particular magnitude of collisions happening in just 1 second. And there are other conditions here you can play around with, but the main idea is to be able to derive this particular unit, which is in this case the unit for collision frequency. As you notice here, you have to follow the agreement, you have to follow the kelvins and everything properly in order for you to show that, hey, this is actually a great way to check for your answer and the operations that you're performing. And take note here that from our previous video, we're able to derive our formula, and by deriving our formula, we're effectively able to, in this case, determine our specific answer for the number of collisions per second for nitrogen gas molecule at that particular attitude, at that particular conditions, by putting those numbers into this particular equation, and in order for we to be able to determine our answer in this particular question. So I hope you found this really informative. Please hit a comment down below. Let me hear your thought about this. But that way I can talk to you soon. Stay smart and believe in yourselves.